Queuing theory, software performance. Thanks for the introduction, Nicole. Yeah, last time I gave this talk, I think was 4.5 years ago. So I added some details in here. They'll be interactive through the beginning to try and help you get your mind thinking about what we're doing. And let's just cut right into it. So this talk is, we're going to explain the basics of queuing theory. We're going to show you logically how it can be applied to software execution. We're going to train you how to use critical path to identify the correct performance issues to improve. And then we're going to kind of go over different techniques for improving software performance and scale, and then kind of walk through the practice of like, how would I actually apply this in practice? So what do McDonald's drive-thrus have in common with software performance? Ooh, French fries are awesome, and fast software is awesome. But awesome isn't what I'm getting at. What I'm really getting at is the principles behind the throughput and latency at the drive-through lane are basically the same as for how computer software works. So, once you start looking for a queuing theory, you basically realize that it's everywhere in the world. We got traffic patterns, you know, like, so when you're entering the highway, why do we have red and green lights, you know, kind of as you're entering the highway? That's actually based on queuing theory and arrival rates. At retail checkouts, you know, for those of you, I don't know if everyone's in America or not, but those of you in America, like the Best Buy checkout, they'll kind of have everybody in one kind of snaky line, and then you kind of split off and then go into each checkout at the same time, versus most grocery stores each have their own separate line for checking out. In project management, and we'll actually talk about critical path because it ends up mattering for what we're going to talk about today. But the actual critical path through the processing nodes are going to ultimately define the duration that a customer is within the system. For food preparation, if you've ever been to, you know, like a Jimmy John's or Potbelly's or Chipotle, they're able to have extremely high throughput and keep you engaged throughout the experience as you basically interact with the people that are preparing your food as you work down in a queue, much like an assembly line. This one is nice just because I'm a graduate of University of Wisconsin. Some dude in the engineering school actually designed an attachment to put onto beer pours at stadiums that were more efficient at eliminating the foam from the beer and be able to pour like 2 or 3 times faster than you normally could. That would like shrink all the lines down at the stadiums. And so it's kind of everywhere. So when you look at in the current world, actually, what's happening with shipping, we're finding that when the systems get messed with one way or another, the lines start to become really unbearable. I don't know if you all, I was mentioning before the talk that I've got work being done on my basement. You know, if you're ordering anything from overseas these days, or almost anywhere, the chances of you getting it anytime soon are unlikely because of the way that shipping queues have been messed up, especially shipping into the United States. This is actually a picture from September where there's just hundreds of shipping containers just sitting outside of the shipyards waiting to be unloaded, which is just another example of queuing theory in action. I can share some of these links later, but the concept of queuing theory and how it's been applied to software has actually been, you know, kind of studied at the academic level, and I've got a couple of papers here. One of them just talking about purely applying queuing theory to the optimization of software systems, but then also talking about the execution of parallel programs on multiprocessor systems, getting into the idea of how queuing theory can be helpful for performance and throughput. So there's a good place to actually just talk about the queue itself and how the whole mechanism works. So there's basically the queue is a fancy word for a line. Okay, so in general, you're going to have customers coming in from you know, at the end of your queue, they're going to end up waiting in the line until they can be serviced by the processor, and that processor will do something, you know, and then you'll exit out the system on the back end. This is how a queue works. So the system time, and I'll use some of these terms kind of throughout here. The system times is the total duration for a single customer. So one of these gray dots that turns into a green dot, how long does that in this case person, you know, sort of sit, or it's not necessarily a person, but I'll be talking about McDonald's lines and things in a minute. But how long does that particular customer exist inside of this system? How long is it end to end for them? And we'll be able to compare that with performance with computer software. Throughput is going to be the rate of completion for customers. So how many customers leave the system at what rate? So we'll be talking about this over the next few minutes in terms of you know, kind of exits per second, or how many customers got processed per second. And then another really important factor for queuing theory, and one that we won't be talking about as much today, is the frequency of the customers entering the system. And that's called the arrival rate. So you've got the arrival rate, time in queue, processor time, and then the exit rate coming out. So the system time in general is that queue wait plus the processing time, and then the throughput in this case is going to be 10 customers per second. Hopefully that makes good sense. I'm going to start quizzing you soon. So so we're going to talk about a special case here. If there is no queue, okay, so if basically there's really nobody in the line, and so that amount of line doesn't take much, take any waiting time, then the system time is basically that processing time, and we can just kind of eliminate all of the queue time, and then the throughput is still the rate of completion for customers. This is going to be useful to us when we're talking about software, because if in a software system, like let's take a website. Okay, in the early days of Twitter, when they first launched, it was, you know, kind of crashing every few days or whatever, because the amount of people that were coming to use the system were overwhelming. Well, in general, with software, if you have more customers than the system can actually support, it will crash, fail. It'll be in kind of this fail state. So while it's relevant to kind of be aware of how things, you know, kind of back up as far as the customers, for the purpose of this talk, and for all intents and purposes for real software systems, if you actually have too much load hitting your system and you can't process it, you know, your throughput doesn't exceed or equal the rate of people entering your system, you will be crashing. And so the techniques that we're going to talk about in order to improve your throughput will help with that problem, because if you can basically get your throughput ahead of the arrival rate, then you'll have a stable system that can operate. And it also helps because the math, when you start thinking about arrival rates and queue time and how those things interact with each other, and this is a big challenge for traffic, you know, like on highways. This is why they put the red and green lights on the entry, on the whatever the merge lane to get onto the highway, is because having a regular cadence of arrival rate dramatically impacts how bunched up the cars are going to be inside of the lanes for a highway. But that's all really complicated stuff, and largely it kind of doesn't matter for us in software, because literally if we have too much load coming in, you have to have a way to either turn it away or your system will crash because it'll get overwhelmed. So that makes the math easier for us to learn during this talk, but it does matter in the real world, and one of the things that we're not going to talk about as much today is actually how, if you're thinking about a CPU processor and then all the things that are going on a computer or multiple cores, the idea of the queue and how things are getting backed up, whatever, start to matter a lot more. We're going to focus this discussion a little bit more on straight line code performance. An example we've got at the end, we'll be talking about things in a browser, just so it's a little bit more kind of accessible. It's also true that back when I started messing with this stuff, we were largely single processor computers, and the way that the systems were deployed, we had to have literal hardware and things like that. Nowadays, it's like, oh, we're overwhelmed, let's just string up another server. And the dynamics of the problem have changed quite a bit. And for us to be able to learn today, that side of it and overwhelming the CPU isn't as important as it once was. Okay. So here's a point. So if you could just, folks, just use the chat on the Zoom, and based on what I've told you, what is so we talked about when there was one processor, the throughput was for 100 milliseconds, the throughput was 10 customers per second. So, and the amount of wait time with no queue would be around 100 milliseconds. So based on what this one looks like, what do you think the new system time will be for a single customer? And then what's the throughput for the entire system? So how many customers are going to be exiting per second? Feel free to just put it right into chat if you have an idea. Ron's got some thoughts. Anyone else? All right, so this first one will be able to help out. So Ron, you're Leon, assuming the processors are in parallel to determine the total time. Yeah, so what ends up happening is for a single customer going through, we're going to say that they just walk right up through the front of the line, so it's almost no time, and then they get processed by one or the other of the processors. So so Ron's spot on saying that the system time is going to be about 100 milliseconds for any one customer. And then the throughput, because we've got two processors coming, and we're going to say that the folks are kind of coming in at the pace that we can support, we have a maximum throughput of 20 per second, because every 100 milliseconds, we're going to process two customers. So 1,000 milliseconds in a second, 20 per second, okay? So by parallelizing the processing, we basically doubled our throughput from that original example, and we didn't decrease the system time for any individual customer. This happens to be an example of how Best Buy, as an example, in their checkout lines, they manage things. I'm going to just mention again the arrival rate and things, but it turns out that having that kind of single queue and then feeding off to multiple processors provides the best, kind of average total system time and throughput. You don't have that problem of like, oh, did I get in the slow lane or did I get in the fast lane? Everything is you're basically, everybody's in the same queue, and they're kind of going through as fast as they can. Queuing theory in action. And so why would it only be double the throughput? So even if there was a large queue being built up, what happens at the end here is that how many processors that are kind of dealing with each customer, it's that exit rate that matters. So even if there was going to be a huge queue behind, well, let's pretend it was like thousands of people in the line, and we've now doubled our number of processors. those processors can't go any faster than what they do. They're going to process customers at the same rate. So when you double the processors, all you get is double the throughput. And then I just got a little mention there that if millions of users are in this queue, the thing is going to crash. The queue is just going to grow infinitely. Okay, so let's take back this similar scenario. Oh, Ron is mentioning that there is some routing overhead time. There's certainly some, like especially in computer systems. We're gonna pretend like that's negligible for the purposes of getting through this talk. Again, simplifying the math a little bit, but it is real that you can't have sort of like infinite processors. Like let's pretend like no, this is true and it's not true, but there's overhead involved with managing all the processors and managing the queue and then routing all the people into the right place. For the sake of our discussion here, while it's real, we're still just trying to learn the basic concepts and then get through things. And most of the time, just understand that basics is going to get you through, like kind of what you care about and what we're generally going to be dealing with. Thanks, Ron. Okay, so let's say that we've got a processor that processes at 200 milliseconds instead of 100 milliseconds. So then what is the new system time going to be for a single customer running through? And then what's the throughput for the whole system going to be in customers per second? And go ahead and chat it away. Double, triple, X times faster. Throughput is still big O, negligible. Oh yeah, I see what you're saying. Yeah, like you have to get really, really big until it's going to start to matter. Okay, any thoughts on or the number of processors? Okay, any thoughts on new system time and throughput? Let's see here. All right, Ron wrote a thing in here. I'm not sure if I'm quite following, but the single customer is going to be 200 milliseconds. So that's the system time for a single customer. That's spot on. And then because we're that exit rate is going to be 1 every 200 milliseconds, we're going to basically get 5 per second throughput. Exactly, Jeff. Thanks. So by having that slower processor by half, we've doubled the system time and decreased the throughput. Oops, I think that should say by half. A little bug there in my screen there. So from an analysis standpoint, if the processor increases time, both throughput and the system time get worse. Okay, so this one we've now split. So we've got 200 milliseconds of work that has to get done. So what happens if we take that work and split it into 2 parts, and now we're processing and processing? So it's the same amount of work as the last one, but what we're doing is we're splitting it across 2 bits and then running them through. So the total system time and throughput. All right. Yeah, I think Jeff's almost got it. Let's see here. All right, no one's quite on. So here's what happens. So the customer has to go through, and so they jump through that first key right away because there's no one in it. The processor, they got to sit there for 100 milliseconds. They jump through the next one, they sit there for 100 milliseconds. So a single customer running through has about a 200 millisecond, about a 200 millisecond wait. And Ron, you're exactly right. That second one should basically never fill because they're both running at the same bit. We're pretending that the overhead is again negligible. Okay, from a throughput standpoint, though, what we're talking about is the exit rate for the entire system. So the exit rate for the entire system is still 1 per every 100 milliseconds. So even though we've split up the processors, they're dependent on each other now. So they have to run serially. And so with that serial dependence, you can't get through both of them any faster, and exiting the system, you're still only going to get one every 100 milliseconds. So the throughput is going to be 10 per second. So if you can split a large running process in half and then kind of jam it through, you could double your throughput. This actually explains why, if you're weird like me and you pay attention to how queues work all over the world, you'll notice that at McDonald's a number of years ago, I can't remember when they started doing this, maybe even like 20 years ago, they started putting 2 windows in the drive-through instead of 1. Okay, so in the old days, so I'm old, so when I was a kid, the drive-throughs only had 1 window, and you'd go up there and you'd like order, pay, and do all the stuff, and you just sit there as long as you would inside of the store. But that processing time takes a long time, and so what they realized is that you could order in 1 window and pay in another. And nowadays they even have you order, into a speaker, then you might pay, then you might pick up the thing, depending on kind of how they have it set up. Your system time, your wait time as a customer doesn't actually change. You still have a lot of the same weights, but the throughput is dramatically better, and the lines can be quite a bit shorter. There's some nuance here looking at the food prep is happening. So there's some parallel activities that I'm not getting into in this example, but it helps. It still helps kind of explain the concept. Okay. So what happens here? Notice how that first processor has jumped from 100 milliseconds to 200 milliseconds. So now what's going to be the new system time? So how much for each customer to wait to get through the entire system? And then what's the new throughput for the entire system? Jack's got a good guess. System time, you're spot on. 200 milliseconds plus 100, you have to go through all of it. So you're going to have to wait the 300 milliseconds. And Tilly's actually spot on with the throughput, where even though that last processor could process 10 per second, they're only getting 5 per second from the upstream processor. So the exit rate, so what's going to happen is that the slowest node in the dependent tree will determine the throughput wherever it is. And Ron's exactly right. That second processor will half the time be waiting. So, five times a second, the first processor is going to kick someone out, and then that other processor will just keep doing them, 100 milliseconds at a time. So it'll basically, process 100 milliseconds, wait 100 milliseconds, because it's only getting them every 200 milliseconds. So McDonald's found that it took much longer for the orders to be taken than the food to be picked up. That's kind of what this is showing here. So like when you grab the food, you just kind of reach out, grab it and go. But order taking, it's like, yeah, I don't know, what do you want, kids? Like all of the kind of back and forth, and it takes a lot longer to take the orders than not. And so what they did, and you see this in a lot of the more modern drive-throughs, is at the beginning of the line, they'll actually have 2 different lanes that you can turn into in order to basically place your order. And so in this scenario, what is the new system time and throughput for each customer going through the system? Yep, Jeff and Tilly, oops. Oh, sorry, I got a bug in my, I added this slide again a little bit late. I'm like, oh, I should do a better, more full example of McDonald's. So the system time is 300, even though my screen says 200, because you still have to go through. So when you're parallelizing, each customer doesn't have to go through each one of the parallels. It's literally copies of the same processor, but they still have to go through it. It's 200, and then they have to go through that last one as well. So it's going to be 300 milliseconds total. And now the second processor can actually, instead of having all that wait time, it can actually take both of the inputs or people from both of those two processors, and then kick them out every 100 milliseconds. And so if you basically parallelize the slow processing node, the exit rates can match those downstream processing nodes, bringing throughput back up. I don't have a slide for this, but what do you think would happen to the throughput if we put a third processor up front here? Yeah, Jeff, you're exactly right. Nothing. What will happen is that second queue will get really big because now we've got an exit rate from the first set of parallels where basically every 200 milliseconds, 3 customers are coming out, but the downstream processor can only deal with one every 100 milliseconds. So it starts to get overwhelmed. And this explains why McDonald's is now using 2 ordering stations for the drive-thrus. Okay, so let's get a little bit more complicated here. There's 7 processing nodes here, and they're each 100 milliseconds each. So what is the new system time and throughput? Jeff is way ahead of us now, and is correct. The each customer is going to have to go through each one of this. These are all dependencies, and so they're going to go 100 milliseconds, 100 milliseconds, 100 milliseconds. They have to go to all the lines, all the processing, and the exit rate for the entire system. Nobody is overwhelmed or starved, so the exit rate is going to remain consistent, and you're going to have customers leaving the system 10 per second because it's processing every 100 milliseconds. So as you add service nodes, the system time goes up, but throughput remains the same. That's not strictly true. The throughput remains the same, but it can remain the same. But, you know, like it'll still be dependent on how fast these processors go, which I think is the next example. Okay, so now we've got the example where you notice that 3 of these processors, the ones in red, the second one, the 4th one, and the 6th one, have all increased. So instead of 100 milliseconds each, the second one is 200 milliseconds, the 4th one is 500, and then 400. So in this case, what do we've got for total system time and throughput? Got some guesses. Tilly and Rye. I wonder if it's 2 people. I wonder if Tilly and Rye are both here. All right, let's see here. You are correct. So what we're going to do is, because each customer has to go through each one, if you do the math, it ends up being 1,500. And the throughput now, the throughput is always dictated by the slowest service node. So basically, if downstream service nodes are faster than upstream service nodes, they're getting starved because the upstream service nodes can't feed them customers fast enough, and that becomes your basically your weakest link. So the slowest dependent node is going to dictate throughput. Okay. So let's pretend that this is a blocking language. I know my notation here is largely like JavaScript, but I don't know, all the languages look the same these days, so it doesn't really matter that much. If we take that same concept that we just talked about, and we're in a blocking language where each line of code needs to finish before the next one starts, which is the way that many systems have worked for years. We'll talk a bit about concurrency and things. So what if each of your processing nodes is basically a call to the system to do stuff? Okay, so if we think about it in that same kind of way, so what is the total system time and the throughput for this system? That's funny, Kevin. We got like 4 Kevins in our. We've got 100 100 or so folks in client service at 8th Light. We've got 4 Kelvins. Okay, 15 node should have 2 times. Oh, you're poking at my code example. I think you're right, because it's going to actually be kind of checking the not error state as well. Okay, so holding aside my my rough cut at like throwing some code in there to try and make it feel real. The latency now is, as you have to go through each one, it's exactly the same behavior that we were just seeing when we were kind of thinking about things in terms of drive-throughs and things. And if you kind of imagine that each stop point, if it, like if we kind of let the queue dissolve away in our head and we're just talking about these dependent times, all of the same principles that we just learned are still going to hold. Okay, so what happens here? So this this middle one here, the remove tow function, was actually reduced from 500 milliseconds down to 100 milliseconds. So now what's the new latency going to be? It was 1500. Yeah, pretty straightforward. We improved it by 400 milliseconds because they're just kind of in that straight line. So if you improve the performance on that slowest service node, or sorry, if you improve the performance on any service node, the latency is going to improve. In this kind of way, I stopped talking about it as throughput per se right here. We could talk about throughput when we're talking about scale a little bit more later. But it helps to kind of like focus in on latency a little bit here. Doesn't the removal of queues make the single 200 milliseconds versus 100 versus the 200 milliseconds? I'm not sure that I understand that question, Jeff. Or does the behavior emerge through parallelization? You can talk, Jeff, if you want.
Okay, how do you get the throughput if each of these goes through in that sequence and there's no queuing between them? Isn't this the case of the 200 more akin to the 200 millisecond with 5 per second versus the 100 millisecond at 10 per second?
Okay, so what you're getting at there is the question of throughput, and you'll notice that I kind of removed the throughput discussion when we're talking about this kind of straight line code like this, because the throughput's going to depend on other things when we're talking about the code, because there's only ever one kind of customer running through, especially like line by line like this. So I kind of messed with the paradigm a little bit, where throughput doesn't matter as much here. Now, throughput is probably going to be constrained by the systems that are actually doing this work, and we can talk about that a little bit more specifically. But I said at the beginning of the talk that I was going to avoid a little bit on the scalability side and like how much some of the parallel processing is going to work. We'll get like how to say, like what I'm basically saying is that when you're talking about throughput, it's hard to apply throughput to a single bit of a few lines of code, and I think we'll get back to it in a little bit when I've got a larger example at the end, and then we can get back to talking about how parallelization can help. And I maybe should clean this up a little bit more here, but what I'm trying to get at is, in general, especially when you got the dependent stream, especially for the straight line latency, improving one of the processing nodes will improve your overall latency. Okay, so how does this help software performance? Okay, so what I'm going to do now is just take a step back. So we've kind of learned a bit about and here's where my timing is rough. We've got about 15 minutes left. We've learned a bit about queuing theory itself, the kind of the mechanisms of arrival rate, the queue, the processor, kind of whatever. We started applying it. We started to think about what matters and what doesn't matter for software. We tried to then give some examples and help you all kind of like do the math yourself so you can kind of visualize and understand. So now what we're going to talk about is how do we actually apply this to systems or like code that we're working on. Okay, so what I want to do is kind of give you a systematic approach that's based on queuing theory and critical path, as opposed to what I way too often see with folks where they're just kind of guessing. It's like, oh, well, we think things are running slow because of this thing over here. And then they just start trying to fix it. And that might help. It might not, and this systematic approach will help make sure that you're working on only the things that are going to matter, and we'll follow that. We'll follow that systematic approach through. So the first step is basically observe the telemetry latency. So throughout whatever process you've got, you want to be able to get measurements of how much time it's taking for each step, and you want to know what all the steps are. So the second part we're going to do then is we're going to map the critical path through those steps. So if you remember back to one of my examples earlier, I said that for McDonald's, I ignored the food processing. We'll not ignore that for our little code example here. It's again a little bit more simplified of a kind of a pseudo example, but we'll show all the things, not just, I think earlier I was kind of just showing the critical path. We'll show how there's code that doesn't matter for how the performance is gonna be improved. And then I'm gonna probably rapidly talk through the different ways to improve performance. This talk isn't so much about that, but I do want to kind of like just talk about like what are the things that you can do in order to improve things. And I really want to get this point across that don't just assume that you're working on the right thing. Don't just assume that because you think you've spotted a thing that can help, that it necessarily is helping, especially in a language with like JavaScript, where some things are happening concurrently, whether you want them to or not, which is, you have to actually build in dependencies in order to prevent them from all happening at the same time. So this first step is observing. Okay, so what we want to be able to do is we want to be able to get some numbers, and we want to be able to basically build the tree. We want to be able to build a similar scenario as we were doing earlier in the talk, but we want it to be all the processing touch points. So whether it's code, there's some network travel, there's queries running on database systems, file IO, whatever the things are that are going to end up taking time. And this is honestly a lot of them right here. There can be some queuing and wait time in some systems. Again, I'm going to ignore that for the time being because your system is probably out of control if that's happening. Then what we want to do is we want to talk about the critical path. Okay, so what is the critical path? Okay, so the critical path is basically going to be the path where it's the dependence. So these are all dependent, running left to right here. Okay, so as the customer kind of going through the process, we actually have to complete every single item in here. But I've drawn the things vertically where they can run in parallel. And we'll talk a little bit about concurrency versus parallelization in a second. But we're gonna basically say that these things can be parallel. So what happens is that the customer has to actually complete every single node in this tree. But what the critical path is going to be is it's going to be the longest run through this set of nodes based on the timing and dependencies. So each arrow is a dependency. When you can do 3 at once, you can run in parallel. and then when they come together, they all the previous ones have to complete in order to stop there. Thinking about like a promise, like a promise all, you have to wait for them all to finish, and then you can keep going. So with that background, and I hope I explained that well. It's a little bit of a tricky concept. The visual might help. Let's see here. So Jack's saying 400 milliseconds. Biggest problem is the 800 in the second group. Yep. I think that's right. So the critical path ends up being these ones that are now marked in red. So the one in the first step, the 100 is the slowest. In the second step, they're all running at the same time, but the 200 will finish first, the 400 finish, and then we have to sit there and wait for the 800 before the 50 can even start. Then when the 50 runs and finishes, then it can run all the next ones. And then the 400 millisecond node at the top there is going to be the slowest one. And so that path through is your critical path through the system. And only improving items on this path will you actually reduce your total latency time. So for example, if we start fixing in this in that second column, the one that says 400 milliseconds, if you improve that to 5 milliseconds, you will not actually change the latency on the system. You will save some system from doing work somewhere, which can help with scalability, but you're not actually going to improve latency because we're stuck waiting on the 800 millisecond item. Okay, then what we want to be able to do then is when we recognize we've got our critical path, so we've observed our system, we've mapped out where the timings are, and we're going to identify where we can make improvements. We're going to do different latency strategies, which includes efficiency, concurrency. We're going to do some scale strategies like parallelism, contention, bandwidth, and we can do both by kind of caching different things where we can kind of avoid work. So you basically skip over a processing node almost, which helps both latency and scale. I'm not going to go super deep into these because we got about 6 minutes off of the main time for this, but for latency efficiency, you can improve your algorithm. You can, identify unnecessary calls, N+1 stuff. N+1 stuff also creates network hassle. Redundant calls, generated code, count your calls, queries. You can optimize your queries. You can add indices. You can change the queries themselves to reduce joins. You can use subsets of data when you can. For concurrency, it's worth noting that concurrency is a bit different than parallelism. So depending on the system that you're working with, and this can matter, especially in the web browser with the event loop, which is ultimately single-threaded. Concurrency is about dealing with lots of things at once. Parallelism about doing lots of things at the same time. So this is from Rob Pike, who's influential in writing Golang. I'll skip over this a little bit. Tony Hoare wrote the original stuff on concurrency. This is all great. If we had the time, here's the picture I want. Okay, so one way to explain it is that concurrent processing, task 1 and task 2 on the left here, are both being managed by the CPU seemingly at the same time. So like the system is managing, it's making it look like they're both processing at the same time, but it's really only one processor doing the work. So it's still doing both sets of work, and you're going to end up, both tasks are going to run slower because they're both, kind of being interleaved with each other, but they will feel like they're happening at the same time. Depending on what's going on, like on a laptop and a web browser, this often doesn't matter because the cycle times are just so fast. But at large scale, it will matter in the end. With true parallelism, task 1 and task 2 are literally running on 2 different CPUs. There's no blocking, there's no interference from them whatsoever. And so the latency on each one, like presuming that the tasks are, running, take the same amount of time to process, they would both be, sort of twice as fast than the concurrent scenario. And your throughput, you'll also have twice as much throughput. So different ways to take advantage of concurrency. One of the major things is to implement solutions that allow for either that allow for concurrency. So like in JavaScript, you kind of actually, like a lot of ways, JavaScript will run concurrently whether you like it or not, but understanding and managing async await is going to help you to be able to kind of control which things are dependent, which things aren't. And then in Rails, you kind of have to go the other way, and you have to actually introduce ways to introduce concurrency, because a lot of the code will naturally be blocking. And then there's other languages that are just concurrent as well. On the parallelism side, you've got languages. It's also reasonable to just have multiple full-on servers so that they're all not kind of hitting the same CPU, even if it's a virtual CPU, and being able to just process more things at once. I'm not going to get into all these contention things, but just a reference of the web browser, single-threaded event loop, watch out page load stuff. You can actually just implement React where you don't have to download the whole page. You can just change little pieces at a time. Be aware of locking queries, table and row, languages that block and not block, and then bandwidth contention is a big one, which like you can have more or faster CPUs, you can have more threads in the servers, more memory per thread, more memory on the server. Okay, I'm going to jump ahead here a little bit because I actually want to do a kind of a working example. We'll see if I can get through this relatively fast. Okay, so let's just say that we've got a web page for the sake of argument, and it's going to kind of run through the stuff that it normally does. So it's going to get the core HTML and JavaScript, and then it's going to start executing the stuff, and it's going to go off and get some user data. It's going to go off and get some permissions and company data. That it'll render the document when it's got enough data, and then let's just say it's a dashboard. So we've got kind of 4 widgets on the screen, and we can got to get the data for metric 1, data for metric 2, 3, 4. And then the widgets would need to render again. So what's a latency? Do you just kind of add it up? Well, no, not really. We're gonna follow our process. We're gonna observe the telemetry. We're gonna map critical path and then improve performance. Okay. So when we're observing, what we want to be able to do is we want to actually know what's happening for each of these calls. So inside of the browser, the user thing's going to go off, and the red's going to go up to the API. It's going to go query the database, and we're going to want to actually see these examples are fairly contrived, and these numbers are actually far larger than I would hope that your system is running at. But the concept of actually observing and knowing where the time is being spent in each thing, because each one of these ends up being a network of queues, basically. And so we'll want to collect the numbers on each. Then from that, and these color codes actually line up the black, red, orange, yellow. This happens to be the diagram that I showed you earlier, where it's like that HTML download. Then we're going to get some data. Then we're going to do that initial page render. Then we're going to get in the background the metrics 1, 2, 3, 4, and then the widgets. You could probably already start thinking about different ways that you could optimize some of this stuff. For the sake of this thing, we're going to say that the critical path is, as we said before, we're going to have sort of 950 seconds till that first render is done. Then we're going to launch these other 4 metrics when the JavaScript is there and everything's kind of working, and then ultimately the widgets are going to display. So the page will be at 950 milliseconds. The widget data will be at 1400. I'm just suggesting that those are in parallel, so they'll happen at the same time. So kind of 1400 milliseconds kind of thing. And so then if we focus in on the critical path items, and it's worth noting that like company there, that's in yellow, if we improve that down below 400, any improvement past 400 would actually not be helpful anymore. So if we knocked that company call down to let's say we eliminated it because we stored the company ID and some data inside of the cookie and the browser, and we don't even make the call to the server anymore. We'd still be then constrained by permission. So even though we got rid of 800 milliseconds of time, we'd only be improving by 400 milliseconds because we'd have a new bottleneck with permissions. So in this scenario, we're just going to pretend, I'm just going to flip back and forth here. You see kind of the changes. We're going to make some improvements. We're going to store something in a cookie. We're going to save something in memory inside of the data store in React. We're going to improve our databases by adding indices. And indexes and databases are really just like code caches that help basically it to process the query faster than it would otherwise do. And we'll do some things in order to be able to make some improvements. And so now the permissions are going to go from 400 milliseconds to 200 milliseconds, and the company's going to drop from 8 to 100. Metric 1 and metric 2, we're going to pretend that those things got better too. And so by focusing in on the items that were on the critical path and then the items that became the critical path later, we're actually now changing the critical path through the system. And now instead of running through 800 and 400, we're actually running through 200 and 200. And the page is going to now render in 350 milliseconds. The widget's going to show up at 400, and then the widget data will show up at 650 because it'll still have to wait the 200 and the 50 in order to go. Debatably, metric 1 and metric 4 would appear first. So anyway, kind of went a little bit rapidly there at the end. Just to wrap up, everything in the world ends up following these kind of same basic principles of the way that queues work, a dependence thing, the times in system, and making sure that you actually observe what's going on so that you can see what the numbers are, and then you can apply the knowledge that you have of how the queues work and how critical path works. And then focusing in on those things that are actually slow will yield performance benefits. And there's probably another talk where we can talk about the implications of scale on this stuff. But the one-liner on scalability is more or less, the more you can avoid a CPU from having to do work, the more the entire system is going to be able to scale. That's from an efficiency standpoint. The other thing that you can do is you can throw more hardware at it. If you have something that, if you can parallelize something and you can process more, you can literally throw more, cloud-based hardware at the problem if it's in the right place and it can truly be parallelized.